Hi. So today we are going to talk about conformed dimensions. So this is the continuation of the module on advanced dimensional modeling, and this is one of the important concepts in data warehousing, because as you know, data warehouse is developed in a bottom-up fashion, right? And keeping in mind the verticals that are there. So as Kimball says that he does not like his approach to be called as bottom up, right? So there is an article also by Kimball called as the bottom up misnomer, so which tells that why his approach is cannot be called as a bottom up approach. But just to understand the things, like when I mean bottom up is what I mean by that is that we first build the data marts and then integrate them at a later point of time. And Kimball says that the integrating framework is in place before you even start working on the first data mart. So keeping all these things in mind, and since we have to do some integration later, right? So it is important that all your dimensions and facts are conformed. Okay, so dimensions and facts conformed means that a dimension can be used, the same dimension can be used in a conformed way with other fact tables. And similarly, if there is a fact that is shared among that appears in different fact tables, it should also be conformed. So let me start by taking you through the topics. So topics for today's lecture include types of types of queries in a data warehouse environment. Just a minute, let me. Yeah. So the topics, so the topics include types of queries in a data warehouse environment. Then there is an operation called as drill across, or an analysis called as drill across. And for this, we would also need the concept of outer joins, and also an NVL function that I'll be introducing. And then we come to, and so these are kind of motivating scenarios for conformed dimensions and conformed facts. So types of queries in a data warehouse environment. So they include outside-in queries. So outside-in queries are basically that you enter the fact table through the dimension table. So that's why it is called outside-in. And then there are inside-out queries. So suppose you want to find out all those products which sold more than 500 units, and you want to find out what those products are, what are those categories, and you want to do some analysis that way. So that is called as inside-out queries, because you start from the fact table and then move out to the to the dimension table. So outside-in queries are like this. It is you move into the fact table, and inside-out queries are that from the fact table you move out, right? And then we also categorize them into fact-focused and dimension-focused. So standard OLAP queries are fact focused. Query touches one fact table and its associated dimensions, so that is fact focused. And then we also have queries that are dimension focused. So what it means is that bring together data from different fact tables that have dimension in common. Okay, and common dimensions used to coordinate facts, and common dimensions must be conformed. And this kind of analysis is called as drilling across. So that's the most common name that we give to this kind of analysis, and that is drill across. So that is one of the topics that are listed for today. So let me talk about a scenario, drill across scenario. So where what we have is a sales fact table with dimensions date, that is customer, product and store. So and there is a customer support fact. So this is a sales fact here, and then we have a customer support. So this is a customer support fact with dimensions date, customer, product and service representative, right? So you can see here that date, customer and product are common common for these two fact tables. So my question that I want to ask is, how does the frequency of support calls by California customers affect their purchases of product X? So this is my setup. So I have two fact tables. One is the sales fact table, and so from where I would find out that who all from California bought product X. And then in the customer support fact, I would want to know how many customers from California complained about this product X, right, or had some issues about product X, and they made calls to the customer support center. So step one is that I first find out the query. I query the support customer support fact and group by customer SSN and filter on state is equal to California, right, and compute count and query result as schema customer SSN. This SSN is the unique identifier for a customer and how many calls he made, and this customer is from California. Okay, step 2, query sales fact, group by customer SSN, filter on state is equal to California and product is equal to X, and compute sum total sales amount and query result as schema customer SSN and total sales amount. Now I need to combine query results. So join result 1 and result 2 based on customer SSN and group by support call count okay, and compute count and average total sales amount. So this is how I will do this analysis, right? So this is just an example of a drill across. So there are 3 steps involved. So first I separately query one fact table, then I separately query another fact table, and then I combine the query results. Okay, so basically this is what I do in a typical drill across query or analysis. So now there are some problems that I see with this particular example. What if some customers don't make any support calls? So if that happens, so there would be no rows for customers in customer support fact, right? There are some customers who didn't make a call. So no rows for these customers in step 1 and therefore no rows for them in step 3. And the solution to this is that instead of doing the conventional inner join, I do outer join in step number 3. So customers who are in step 2 but not in step 1 will be included in the result of step 2. And attributes from step 1 result table will be null for these customers. And these nulls can be now converted into an appropriate value or a string using the SQL's NVL function. Okay, so I'm now going to tell you a little bit about outer join and the NVL function, so that when you do report generations in a data warehouse environment, you can use both these features, right, to perform drill across analysis, right? And later, like once we have understood this example, we'll be introducing conformed dimensions and conformed facts. So outer join, so let me clear this annotation. So left outer join or inner join, select rows common to the participating tables of a join. So this is the conventional join as we denote it like this, right? Okay, selecting elements in a table regardless of whether they present in the second table or not, right? So the solution is outer join. So in Oracle, so this is Oracle specific syntax, right? But this may be different in a different RDBMS. We'll place a plus sign in the where clause on the other side of the table for which we want to include all the rows. right? So here we wanted to put it along the customer side, right? So I'll put a plus customer thing. So let me show you this to an example. This is a different example altogether, but it explains the auto join very nicely. Yeah, so you have a store information. So there is a store name, sales, and date. So this may be for a product or the total sales in that, right? And then we have a geography table where you have the region name and the store name. Okay, so you can see that store name is common in both these tables. So we want to find out the sale amount for all of the stores. So if you do a regular join, okay, so you will see that we would have missed New York, because New York on the dates that we are interested in, there is no sale in New York. So because it does not appear in the store information table, right? So what we do is we perform an outer join, and I want to include all the rows of geography. So I'll put a plus sign in geography, right? So you can see here, so what I am doing is select A1. So A1 is the alias for geography, and select store name, sum A2 sales, and we call it sales from geography A1 and store information A2. Okay, I'm performing a join here. So this is a conventional join up to this point, and you can see we are doing the join on store name, right? And A2, which is which is store information, right? I'm putting a plus here, and group by store name. So when I do this, right, so what do I get? So there are 4 stores, okay, and A2, yeah. So sum A2 sales and A2 is store information. So you can see now that the result of this query is like this. So Boston, you can see, is 700, so it is coming. New York, there is no record here in New York in this, so this has to appear, but here it is a null. And Los Angeles, so you can see there is a record, so it's a Los Angeles, there are 2, so I am grouping by the store name, so it is giving me 1800. And similarly San Diego has 1, so it is giving me 2500. So this is how what I get. Actually this okay, wait a minute, this store, it should be from the geography, right? So I want to, so this plus should be on this side. Okay, just make this correction. So now this is what I get. Now this null, I can interpret it in any way, right? Probably I'll feel that there is a the value, the sales were there, but the value is not known to me, right? So to remove this ambiguity, what we do is we use a NVL function, so that I introduce in the next slide. So what this NVL does is, whenever it encounters a null, right, you can specify what should be the value in place of null. So whatever value I want, I can put here. Okay, so let us see how it works in the next slide. So in Oracle PL/SQL, the NVL function lets you substitute a value when a null is encountered. So it is basically its standard format is string 1 and replace with. So if string 1 is the test string for a null value, and replace with is the value returned if the string is found null. If the string is not null, nothing happens. So now let me give you some certain examples on this. So select NVL, supplier city NA, right? So if there is no value in the supplier city, right, then I would replace it by NA. If the supplier city is found to be null, so instead of null I'll write not applicable. Okay, let us see another example. So this is an example where I replace it by a string. Select example 2, select supplier ID, supplier description, supplier name from suppliers. So what it says is that if supplier description is null, then replace it by the name. So this is again the same kind of example. Now the third example is slightly different. So commission, if the commission value is null, right, say for example I suppose don't know the value, right, so it will appear as commission and then a null, right. So this is how it will appear. Okay, so this SQL statement would return 0 if the commission field contained a null value. Otherwise it would remain the it will return the commission field. So I can replace it by a string, I can replace it by any value that I want. So this is how NVL function is defined. So in the previous example, I would use, say, if sale amount, if sales and 0. So NVL in the previous store example. So if sales is found to be null, it will be replaced by 0. And once I do that, I get an appropriate report. So here I would get, in that case, a value $0. Okay, so that is more, that looks better than this, right, without anything against the sales, right. So now let me come to what are called as conform dimensions. So dimension tables conform when attributes in separate dimension tables have the same column names and domain contents. That is, their context is the same and they have the same column names. And information from separate fact tables can be combined in a single report by using conform dimension attributes that are associated with each fact table. And conform dimensions are reused across fact tables, and we have already done the ETL subsystems. So I want you to refer back to ETL subsystem 8, which talks about conforming, which is a conforming system, and it conforms the dimensions and it conforms the facts that are there. And more on this later, that conforming dimensions is the major task here, and most of the time is spent on conforming dimensions. And conforming facts is relatively simple and it takes less time. So I'll give you some figures. So this is what I explained at the beginning of this lecture. So conform dimensions, bottom-up data warehousing approach builds one data mart at a time, right? So drill across between data marts requires common dimension tables, and common dimensions and attributes should be standardized across data marts. So what we do here is create master copy of each common dimension table. So what we do is we create a master copy, and then from the master copy we create replicas, right? So I can create multiple, right? So I'll explain this. So I can have a copy, right, a dimension table which is identical to the master copy. That is one situation. Then dimension table has subset of rows from the master copy. So only a few rows are selected. So can improve performance when many dimension rows are not relevant to a particular process. So suppose I am doing an analysis with respect to a branch. So only the branch customers of that branch should be there in that dimension, right? We don't need customers from other branches to be there, right? So that way I'll reduce the number of rows in the dimension table, and that would also help me in speeding up the query. And dimension table has subset of attributes from master copy, and this allows for roll up dimensions at different grains used in, and this is typically used in aggregation. Aggregation is covered in detail in module 7. So there you would understand this. So basic idea is that suppose I have a product dimension, and I want to roll it up to, say, product. I want to create an aggregate, or I want to do a roll up analysis from product to subcategory and then to category. Now whatever attributes that apply to the product and to subcategory may not apply to or will not apply to category field. So what I have to do is I'll have to remove certain attributes, like for example product name, product description, product size, product dimensions, right? Okay, so all these would not apply, right? So for subcategory also there can be certain attributes which do not apply at the category level. So as we move up the hierarchy, right, certain attributes do not make any sense. So we have to remove those attributes. So once we remove those attributes, So those then also the dimension is called as conformed. So there are three situations. One is an identical copy, second is subset of rows, and third is subset of columns or attributes. So in these three cases, situations, we call a dimension as conformed dimension. Now let me give you an example of conformed dimensions. So monthly sales forecasts have to be made, and predicted sales for each brand in each district each month. So point of sales fact table is recorded at a finer grain detail like daily. So right, so what I'm looking at is product SKU versus brand. So there is a hierarchy from product to brand. So I don't want to work at the product level, I want to work at the brand level. Similarly, in the time dimension, I don't want to work at the daily granularity, I want to work at a monthly granularity. And similarly, I don't want to work at the store level, I want to combine all stores into a district, right, all stores in a particular district, and do an analysis with respect to district. So we use roll-up dimensions, which is one of the types of conformed dimensions. So brand dimension is rolled up version of the product dimension. So you can see brand to product, one row per brand in the analysis, and only include attributes relevant to brand level or higher, right? So as I told you, whatever apply at the product level may not apply at the brand level, right? And month dimension is roll up to date. So when I use month instead of date, what happens is that weekday, weekend, special event, all those things would not apply here, right? So I'll have to remove certain attributes from date dimension to come up with month dimension. And similarly, whatever attributes apply at the store level, like store manager, right? So there are multiple stores in a district, so store manager, store address, right, and store location, address and location is same, right? So all these things would not apply at the district level, so I remove these attributes. So in whenever I'm designing a data warehouse, so I must make sure that when I create roll-ups, right, or when I do a roll-up analysis, right, only the conformed dimensions are used so that they can be shared. We don't need to make multiple copies of these and maintain multiple copies of the dimensions. So there is a way by which we can use the same master copy and make copy and master copy and share it among the different fact tables that we have. So let me clear this. So if the same measurement appears in separate fact tables, care. So now let me turn our attention to facts, right? If the same measure appears in separate fact tables, care must be taken to make sure that technical definitions of the facts are identical if they are to be compared or computed together, right? And if separate fact definitions are consistent, conformed facts should be identically named, right? Otherwise they should be named differently, right? And examples of this include revenue, profit, standard prices and costs, measures of quality and customer satisfaction, and other key indicators, right? Key performance indicators are the facts that must conform, right? So because they may be shared across different processes, right, across different fact tables corresponding to these processes, and if they are not conformed, I'll not be able to do any kind of comparison between them. And if they are the same facts that are being shared, then I must make sure that I name them identically, right? And as I said, designing conformed facts is not that big a challenge as compared to designing conformed dimensions. So what happens is that 90% of the data architecture effort goes in designing conformed dimensions, and only 5% effort goes into establishing conformed fact dimensions or definitions. And this is another example of drill across, right? So here again I have given you some idea about the conformed dimensions. So you can see That question is, how did the actual sales diverge from forecasted sales in September 14? So there is a forecast fact and there's a sales fact that I'm using, and it is very similar to the example that we did earlier. So there's nothing new as such, just for just I wanted to include one more dimension here. So and here you can see towards the end, you can see that forecast exists for every brand, district and month. So this is basically that sparsity concept that is again coming in. So so I'm saying that I'm assuming that forecast exists for every brand, district and month. So it may not be there for every date or every store, right, or every product, but at the aggregated level, at the brand, district and month level, it must exist. And every brand has some sales in every district during every month. So this is like so when we discuss aggregation in module 7, right, you will be able to understand this much more better. So I'll just put a reference here from module 7, and where we talk about sparsity and sparsity failure. So with this I conclude this particular session on conform dimensions and facts. And once you conform, right, then all the analysis like drill across or any other analysis that you want to do is simplified to a very great extent, and it is one of the important design steps in a data warehouse. Thank you.